there needs to be more musical theater at PyCon. It is my 7th PyCon. Scary thought. We're getting older. Ladies and gentlemen, just a quick reminder before we get started this morning. If you have a device that makes annoying noises while the rest of the room is silent, it'd probably save you a fair bit of embarrassment if you made it silent now, so please do that. But you can keep talking amongst yourself until we actually get started. Don't be quiet on my part. Starting until that door closes. It's on its way to closing. So in this venue, the doors don't sit open. It's hard. It's not easy for people to walk right. That will make the hallway track sound. I don't know if it's going to close. No, it's closing. Just people are pushing it open. Well, Mr. Cameraman, are we ready? Great. Oh, hello everyone. Welcome to the morning session of the Friday of PyCon 2014 here in Montreal. It's great to see so many of you in this room. So, our first presenter today is here at his 7th PyCon. He's been using Python since 97 or 98, he's not quite sure. And tries to share everything he learns with the community that has given him such a great programming language. I think you've chosen a really good presentation and presenter to come to see first here at PyCon. Please welcome Brandon Rhodes.
Well, thank you. Welcome everybody to PyCon. I'm glad that you've all made it safely, and I wish safe travels to any who haven't arrived yet. I'm Brandon Rhodes. This is my talk, All of Your Ducks in a Row, Data Structures in the Standard Library and Beyond. a sort of beginner to intermediate level talk because very often people complain that they don't hear until very much later about useful data structures hiding in the standard library. There's a lot of them that I didn't know about. And so this tries to get them all into one slide deck and all into one place. What are the purposes of this talk? You know, in case you're thinking of walking next door to one of the other excellent talks, it's good for me to put this at the beginning. 3 main points. How do data structures work? How are they actually implemented in memory, and why does that make some operations efficient and some slow? What can they do efficiently for us? And then finally, I will reveal which data structure is Python's most dangerous. In fact, I will reveal it right now in case you really want to be listening to one of the other excellent speakers. It is the list. To find out why, you'll have to wait a few minutes. Computer memory is an array of bytes, little integers that can have 8 binary digits and hold a value from 0 to 255. Bytes in memory are named by sequential integers called addresses, and your processor in your laptop or tablet asks for byte number 5 and gets it back from memory. To save space, I'll be writing bytes in rows of 8, but they are simply a continuous sequence with no break in the computer's hardware. Now, RAM chips are the one massively parallel computing device in your computer, which is what provides you random access to a billion different locations without having to wait for a billion locations to be visited. It has a grid of lines that it uses when you throw an address at your memory chip. It makes like a billion simultaneous decisions so that all 999 million locations that aren't being asked for their data at the moment kind of put their heads down, and the one location whose address lines have just all lit up green puts its value on the outgoing data bus. A massively, massively parallel computation that does gives you a billion answers at once. That's how you can get to memory locations with equal speed. This talk will ignore a lot of the complexities that now exist between the chip, your processor, and RAM. Both the question of compression, the bus to RAM is now so slow compared to your processor that many researchers are compressing their arrays in memory because the processor has ages to decompress a block that it gets once it finally comes in from RAM. And I'm going to ignore memory hierarchy, but I strongly recommend you see Gustavo Duarte's What Your Computer Does While You Wait blog post and Dan Liu's blog post very recently, How Misaligning Your Data Can Increase Performance 12 Times, along with a sample script where you can see that work. Why do I ignore those issues? And it's supposed to be a fairly technical talk? Because the standard library does. Lists and dictionaries don't pay attention to memory hierarchy very much at all, and so I will follow suit. All right, I was talking about addresses, these numbers that are used to index memory locations. Since they are integers, you can add and subtract from one address to visit another address that sits near it. Address arithmetic, then, is used to support the 2 fundamental data structures at the machine level, which I will call records and arrays. A record is just when you put some fields, some information, in an agreed order in memory. Every Python object in your CPython memory store always starts its record with 8 bytes of reference count on a 64-bit machine and an 8-byte address of the type, the integer type that has all the integer methods, or the floating point type that has all the floating point methods. So this is, I checked, this is how an int is actually laid out on my 64-bit machine at home. 24 bytes, of which only 8 actually contain the integer. Floats are laid out similarly, but use a different format so they can store a floating point number in their payload. And some Python data structures are of variable length. Here is one way of storing a string. It has 6 different 8-byte fields before it then actually includes the payload, the actual string that I want to store. Given a record, you retrieve a field by adding the record's start address with the field's offset. Again, very simple arithmetic involving these addresses. So if I wanted to get the address of this integer's type, I get the beginning of the record's address and add 8. If I want to grab the integer payload, I add 16. And if you know the layout of the record, a simple addition will let you get to any element in it instantly. This is used to create a data structure at the C level that is also exposed by Python called struct, and this is the name of the module you can import. It lets you, you use a little formatting string, IIF in this case, for integer, integer, float, to describe the structure that you want to build, and it actually builds exactly that C structure in memory and lets you get those three objects, 2, 9, and 20 in this case, rebuilt later. A struct can be very useful for having a binary conversation with a C library or doing I/O where packets require a certain layout. But it's typically only for very low-level operations. The other low-level data structure that Python exposes is the array. How do they work? In an array, unlike a record, everything in it is the same. Everything in it is the same length. And so, in a simple string, if we want to get the character I, we get the address of the first character and add I to the address. If instead it's a Unicode string and is using 4 bytes for each character, then the additional characters live at A plus 4, 8, 12, 16, and 20. And in general, if an array item is B bytes long, you can instantly get to any item I simply by multiplying B times I. It's random access, instant access, just like your computer's memory. And so these are sort of complementary approaches. In a record, you add the offsets that you've memorized to your fields to get heterogeneous data where everything means something different. In an array, you use a multiplication to get to homogeneous information. Each element is the same length. Both, by writing on top of that memory chip's massively parallel architecture, gives you immediate access to the data you want. There is an array module inside of Python that gives you a type similarly named the array. And it, if you give it some information, will pack it into memory as long as they're all of the same type. You can modify the elements and then pull them back out later. Very useful, again, for binary conversations with C libraries or I/O. It packs data very tightly, and so Python has a lot of specialized arrays in addition to plain old vanilla arrays, strings, Unicode, and a number of other data structures you probably use every day are implemented at the machine level as a simple array. That's why indexing is fast. But accessing the items of an array requires repeated building of objects to represent the values. If I'm going to iterate over an array of floats that you can see down there at the bottom, Python's going to have to build a fresh float object to let me see each of those values. To sum an array of 100 floats in Python, Python's going to have to build more than 100 float objects that are then thrown away, because all I want is the sum. This has led to the invention of an incredibly powerful library called NumPy, which is now the basis of nearly all scientific and data Python computing. Python arrays, they're very simple. For C or I/O, a NumPy array is what you use when you're doing math. NumPy arrays support math operations directly between arrays and scalars without needing to build intermediate Python number objects. So if I make a range of 5 numbers and ask for the sum, Python only had to allocate a single int to give me the answer. All of the computation occurred internally, and here I spin up 2 additional arrays, one built with multiplication and one with addition. Neither of those even created a single Python number object. They happen directly at the C level. Use NumPy or a similar library with more of a data orientation called pandas if you need to do math on millions of numbers without needing millions of Python objects. There's also a replacement to NumPy that's on its way that you might also want to look at called Blaze. Note that if you use PyPy as your interpreter, it can auto-detect if you have built a list with only ints or floats in it, and might, if it wants, substitute a fast array for it. Python itself, though, now we're going to sort of pivot here. It can't use raw records or arrays for most of your data structures because it's a dynamic language where everything is an object and where you're not required to build lists, where everything is the same. So Python's main data structures are going to be general purpose. They need to be capable of holding any object. The tuple, for example, which we'll start with, I can throw ints, floats, strings into it without caring how big they are. How are those three objects going to fit when they're of different sizes? How am I going to find them in memory if they're each of a different length? Array address math that we looked at a few minutes ago, which is very fast, depends on every element being the same number of bytes long. How is this going to work? Well, you'll remember, David Wheeler once said, all problems in computer science can be solved by another level of indirection, so Guido added one. A tuple does not store your objects in line in the data structure. It has an array of addresses instead that tell it where to go look in memory for each of the objects that you've stored. This is indirection when you store an address rather than the thing itself. You can say to your friends, I use Python, the language that gives you data structures without any of the actual data. All of Python's general purpose data structures, we'll see, just store addresses and leave the objects off somewhere else. This means that moving an item in one of these data structures only means copying an address. Your actual floats or strings never have to get moved around, which is efficient. It means that there's only one copy of an object, regardless of how many times it appears in a tuple, list, or dict. If you keep reusing that string, it's just the address that's getting copied to each new data structure. So, given the layout of the tuple that we saw, grabbing its length or grabbing an item is just a single fetch. And so, and there is, by the way, in the collections module, a named tuple if you want something with the efficient storage of a tuple, but that gives you something more convenient than integer indexes for accessing its items. Tuples are read-only, a sequence of objects that is zero-based, the simplest of Python's general-purpose data structures. And note that because a tuple knows its length, it can do bounds checking. That might be important to you someday. The next data structure up is called the list. Lists are like tuples, but they're interesting because they can grow. And the problem is that once you've allocated your list and then probably put some other objects subsequent to it in memory, it's hemmed in. It has data already allocated on both sides of it in that array of your computer's memory, and it would now need to move if it needs to grow by another element because there's no extra room. Well, you know, there is this guy. Because, by the way, the reason you can't easily move the list is all of the other data structures and names that reference it just hold its address. So if you move it, they won't be able to find it anymore. So there's this guy named David Wheeler, and he once said that all problems in computer science can be solved by another level of indirection. So that's what the list does. All it holds is its length, the size of its storage, and the address of the block where it puts the real addresses that then point to your list items. So 2 levels of indirection can solve the problems that 1 level does not. Now, why did that list, I'll bring it up on the screen here again, have an extra 4th slot? If the list is of length 3, why has Python wasted space by having a blank element? The answer is that if a Python list reserved no extra room, then every single append you did would require a reallocation. Reallocation is expensive. Each item address has to be copied to its new home when you reallocate to a new free area of memory. So reallocation on every append would add up. If to add the 2nd element, I had to copy the 1st's address. If to add the 3rd element, I had to copy the 1st and 2nd's address. Then you can see that a length of just list 10 appends would cost 45 address copies. A 1,000-element list would require 500,000 operations, and a 1,000,000-element list would require a 500 billion copies of an address in memory. This is my standard, by the way, 1,000 and million thought experiment that I do to check whether my algorithms are going to slow down when their data gets big. I think, what's the cost of doing this operation 1,000 times and 1,000,000 times? If the answer grows zeros at twice the rate of the question, I lose, because a trillion is a bad, bad number. And in general, as you watch, how many operations will you do at 1,000 and how many at 1,000,000 objects? Your computer science friends will tell you that there are formal names for what happens if an additional 3 zeros gives the time 3 zeros, 4 zeros, or the very horrible 6 extra zeros. Why is a trillion horrible? 1,000,000 seconds, as an analogy, is 12 days. PyCon, from setup to tear down, about 1,000,000 seconds. 1,000,000,000 seconds is 31 years. There are people in this room who have not yet lived 1,000,000,000 seconds. A trillion seconds is 31,688 years. If a trillion seconds ago you went to the Bering Strait, dress warmly, you would be waiting 20,000 years before the first band of hunter-gatherers would walk past you from Asia and become the first humans to enter the New World. That's how long a trillion is. So, how does the list get out of this problem? An append on a full list doesn't just add one slot, it adds several. And the list goes through a series of expanding sizes. Designing a data structure in this way is called amortization because it spreads the cost of reallocation over a lot of time, just like a mortgage does for a loan. And so if you build 1,000, 1,000,000, or 1,000,000,000 element list, the number of reallocations stays under control, and thus you'll notice the number of address copies only grows by about the number of zeros you're adding to the size of your data set. That's very good performance. Now, amortized costs do tend to be bumpy. When you add the 991st item, the list is going to jump up to 1,120 slots, and that particular append will be a bit slow because the list gets copied to new location. But in return, the next 130 items get appended at no additional cost. That's called amortization. The Python list then illustrates a trade-off. To save time and not have to do a trillion things, we have to waste space in almost every one of our lists by the fact that there'll be some unused slots at the end. This is the classic speed versus space trade-off that all of computer science imposes on us and requires us to think through. Python lists, I did a little measuring, on average use about 94% of their slots, so they're consuming 6% more space in order to be very, very fast, what we call linear time in computer science. So why did I say then that the list is Python's most dangerous data structure? It's because, I think, in the new programmer's mind, they tend to look at whether an operation they're doing involves one item or many. Here are some single item operations on a list. Here are some several item operations on a list. And it makes sense to us that if we have an 8-character list and do something to all 8 characters, it'll take about 8 times as long as a 1-character list. Problem. Some of the single item operations have to touch every single item in the list without the naive programmer being aware of this. If you append to the list, for example, very fast. If instead you insert at the beginning, you'll be waiting at the Bering Strait for 20,000 years waiting for your algorithm to finish. If you pop from the end of a list, very quick, because that's where it's built to adjust. If you pop from the beginning, the address of every other item has to be shifted over one slot every time you do it. That's why I often see people trying programming for the first time want to visit the items in reverse order like this and wonder why a simple few thousand items takes 18 minutes or something. This is how we would do it in idiomatic Python instead to avoid that penalty. The list is Python's most dangerous data structure. If your friend comes to you and says, I've started learning Python and my program is just sitting there waiting for the next ice age, look and see if they're using a list. Slicing deserves brief mention Because the slicing operation, a type can choose whether it wants to copy the data or generate a view. Normally in Python lists, when you slice, an entirely new list is created, but that's expensive, and that annoys both scientists with lots of data and data scientists. And so NumPy and Panda slices are simple views that copy no data. They're like a little fake list that when you ask for element 50, really goes and grabs element 450 of the original sequence. Therefore, they're very fast and very efficient. All right, now we come to the dict, which I won't give a lot of detail on because of a talk I did earlier. I'll just say that while a list doesn't give you any choice of names, they're going to be integers, a dictionary lets you choose the keys that you want to look up data with. Behind each dictionary, to implement this, is an array, because that's the one thing the computer does efficiently, in which keys are stored at an integer index that's built from something called the key's hash value. So that translates for us from something complicated, a key, to something simple, an integer. So each slot in a dictionary has to keep both the key, to remember what it was, and the value. See my PyCon 2010 talk, The Mighty Dictionary, for a colorfully illustrated entire guide to how the dictionary works and amortizes costs. I will say here only that it grows, because I know I showed you with lists to worry about this. It grows by doubling or quadrupling its size, so the resize costs are amortized, as they are with the list. It resizes at 2/3 full, so there won't be too many hash collisions. And therefore, it's only ever 1/3 to 2/3 full. The slots in your dictionary, at least 1/3 of them are empty at any given time. It's this classic speed versus space trade-off. If you want to get to a dictionary item instantly, you've got to give something up, and space is what we give up in Python. Given a key, a dict hashes it and can usually jump right to its slot. All dictionary operations are fast and therefore safe for beginning programmers. Takes 1 unit of time to hit one element, n units of time to hit all of them. Very obvious and simple and well-behaved. Common tasks that we do are joining, counting, grouping, whenever we have unordered data that we want to get associated instantly and correctly. And because this is such a common pattern, you'll find in the collections module a default dict so that you can just, for example, append to a key without even worrying about whether you've put a list there yet. You can have the default dict put your lists there just in time for you to append to them right when they're created. And thus we've grouped these animals by their, whether mammal or reptile. Because it's so common to do that with integers to count, there's a counter class that you can give it a phrase and it'll tell you the most common letters. You can give it a list, it'll tell you the most common items. Remember, you can build compound dictionary keys with a tuple if a simple integer or list isn't a sophisticated enough key for you. If the order of the items doesn't matter, let's say we're looking over a slate of projects to see what languages tend to be used together, use a frozen set because those are not sensitive to order, or of course sort your keys before turning them into tuples, but I prefer sets. Because the dict assigns each key to an array index by a hash, it always forgets its order. It iterates in arbitrary order, and thus you see the list and dict are kind of the opposites of each other. The list only does order and does it really fast and well. The dictionary only maintains the association and throws out the order. 2 data structures, 2 superpowers. What if you want both? Then there is an ordered dict in the standard library. You'll find it in the collections module, and it, when you iterate later, remembers the order that the keys were added in if you need that. It's great for things like header fields, JSON data that you want to print back out in the same order later that it came in. There is a set built into Python. It's just a dictionary with only keys but no values, and it supports all of the set operations you might have learned in math class at very high speed. Very obvious, very little danger. Classes, I should mention, are by default implemented with a dictionary. Each attribute is a key in a hidden dictionary, but you can turn it into a record. You can turn it into one of those really efficient data structures I showed you at the beginning by pre-specifying slots. I'll let you look that up in the documentation if you want to know how to have millions of objects that are stored a bit more efficiently. Well, I mean, those are the main data structures. Those are our workhorses. Those are what we use. What's left? A few other little topics I'll touch on here. First, dictionaries lists are great for grabbing one thing or iterating over all the things. But what if you want to fetch a range of things? You can sort a list or array and use the bisect module. You can say, let's say I want all the numbers between 3 and 4, and it does a really efficient binary search, narrowing in very quickly on where that range begins and ends so that you can pull it out of your list or array. Sometimes we want a list that can be modified at both ends instead of only the right. There is a deck built into the collections module that instead of just supporting append and pop at the right end, which by the way gives you what's called a stack, which is a very natural way to organize tasks inside of tasks that you need to do, the deck lets you modify both ends with an append and an append left, a pop and a pop left, and since you can put items in one end and take them out the other very efficiently, it is the data structure secretly behind the queue, which is a deck with locks on it so that your threads can all cooperate and send data or messages to each other. What if you need to do a popularity contest? You have lots and lots of elements, and you just need the top 10 or the top 100 without the expense of sorting the entire sequence. There is a heap queue that lets you fetch the top T of n items in only linear time on T and n. You just get some sequence, you heapify it. It does a little like tournament elimination contest to get them ranked into tiers of more and less sorted information, and then can pop and push very, very quickly. And the module goes ahead and gives you an n largest and n smallest callable that does all of those steps for you to get the 100 biggest objects without having to sort all million items in your array. There's a priority queue, also, I believe, in the queue module, which is a heap queue with locks so that threads can cooperate on prioritized work, where the work is labeled with priorities that make some items come off of that queue earlier than others. There's also a scheduler module that uses the heap queue. You can give it items on your calendar or events on your server that need to take place, and it'll tell you how long to wait until the next one triggers, using, again, this really efficient heap queue. So, where are all of the old-fashioned data structures? All the ones you read about in Donald Knuth, Book 3, the linked list, the doubly linked list, and all of the trees. My suggestion is this: you don't see them in Python code because they make very little sense when our data structures no longer contain data, but only addresses. You see, back in the old days, you would build the linked list by actually putting the links in with your data, which wasn't that big a deal. What's the cost of one extra link when you have this big record sitting there? But in Python, where everything is an object, a linked list only consists of another address together with the links. It's much more efficient to just have a list and put the addresses all together. Both the deck and the ordered dict do secretly have doubly linked lists inside for their accounting, but all the other linked lists that you're really using in production are hidden in your memory allocation layer. Since your Python objects are already allocated by malloc inside of a secret linked list, it's just kind of redundant to try to do memory management all over again by your own level of linked list. Trees only really exist where our data is tree-shaped, like MIME messages inside of other MIME messages, XML elements inside of others. All the old traditional uses of trees, then, and this is the last thing I'll say, trees do, besides representing tree-shaped data, they are used very often to represent sequential data that's constantly changing, that has stuff coming in and out that needs to be kept in order. We have outsourced the trees to our data persistence layer, to our databases. They all have trees inside of them for indexing. The data systems of yore were long-running and might keep a data structure around in RAM for weeks and need the maintenance that a tree gives it. But our programs today tend to be episodic, concerned with a view, an update, a report. which turns us towards a functional programming style that involves quick write-once, throw-away data structures that we create with comprehensions. We don't very often maintain a data structure. We don't very often keep a list around and keep modifying it all day long to keep it in the shape we need. We've outsourced that to our storage layer. If simple data-centric code, functional code is indeed the future, as Uncle Bob Martin and Gary Bernhardt recently suggest, see my 2013 talk, The Clean Architecture in Python, then simple, elegant lists and dictionaries are exactly the data structures that will be taking us there. Thank you very much. Alas, there is no time for questions. I'll see you in the hallway.
Everyone, please thank Brandon again. Right, we're going to adjourn for 10 minutes. We'll be back at past for our next talk. So see you then.